There is another nice notation that many people use for vector field integrals. So in this context, let's stick with 2 dimensions. So we have a vector field with 2 component functions, m and n. So for a flow integral, right, this is, if we parameterize this, it would be f dot r prime dt. Another way to write that would be f dot, right, r prime is x prime comma y prime. And if we felt like it, so this is a weird thing to do at first, but if we felt like it, we could treat this dt like a scalar, which it is. It's an infinitely small scalar, and do the scalar product with r prime. And that would put a dt right here and right here. Okay, now f is really m comma n. Okay, so we're going to dot that with x prime dt comma y prime dt. Okay, that gives us the integral of m x prime dt plus n y prime dt. But, so here's the point of this exercise, x prime dt, that's dx, right? Since x is really a function of t, dx is the derivative of x with respect to t times dt. So this x prime dt, that's dx. Plus, and then the same thing happens over here, n times y prime dt, that's dy. So sometimes you'll see people write vector field integrals like this, as long as you remember this relationship, which, right, this is kind of a key to calculus, this relationship of differentials. As long as you remember this relationship of differentials, you'll always remember that when you have a parameterization, dx just means x prime dt, and dy means y prime dt. Okay. For the flow integral, this is fine, I guess, but it's maybe not a huge benefit because we had a very nice way of expressing the flow integral. But for the flux integral, it's a little different because, right, this vector n, there's no nice way to write it, right? For the flow integral, we just get this r prime sitting here. But for the flux integral, we had to like write out explicitly this perpendicular vector that pointed to the right. Yeah, this y prime comma minus x prime vector, right? Which is sort of weird. But if we play this game that we played with the flow integral, for the flux integral, we get, right, f is m comma n, and then we need dot that with y prime comma minus x prime dt. And then when we do this dot product, we get the integral of m y prime dt minus n x prime dt. And so this flux integral, one nice way to write it is m times, there's dy minus n, and then here's dx. So this is one nice way to write this flux integral. Some people prefer this notation. People that work with vector fields heavily, sort of in some contexts, need to be able to express integrals involving vector fields more flexibly, because this and t aren't the only vectors that show up, and this notation can be handy in those contexts. So I think our textbook does use this notation sometimes, but not very often. But I thought I'd mention it just to give you. Yes. So now we have one more item to add to our list of, right, what the flow and the flux integral is. So the flow integral is the integral of m dx plus n dy, and the flux integral, another way to write it, is the integral of m dy minus n dx. Okay. So using this notation, let's evaluate this this line integral around this curve. You can see that this is just a circle with radius 2, and we're going to go around it counterclockwise like this. So we need to parameterize this, right? To evaluate this, an integral expressed in this notation, you do still need to parameterize it. So for our parameterization, let's see, we're parameterizing a circle with radius 2, so let's use 2 cosine t, comma 2 sine t. So r prime is going to be minus 2 sine t, comma 2 cosine t. And remember, what we wrote this down because we need x prime and y prime. So now we can parameterize this. To go once around the circle, we need to go from 0 to 2 pi. Okay, so now we're just going to write out all of these bits, except we're going to use x, y, and x prime and y prime to whenever we encounter x, y, dx, or dy. So y is 2 sine t. Okay, now we need to multiply by dx, so that's going to be x prime dt. Right, so x prime is minus 2 sine t dt. Let me put this in brackets. Plus, now we need x times y, so that's 2 cosine t times 2 sine t, okay, times dy, and remember dy is y prime dt, so times 2 cosine t dt. Okay, so there's the parameterized integral that we get. Let's not actually calculate this. Right, you can see, as usual, once we've parameterized the integral, it turns into a single variable integral. So I'll let you work out what this integral turns into if you're curious.